Okay, so now I'm going to talk about a concept called an expressively complete set. So the definition of an expressively complete set is that a set of logical connectives, that is logical operators like AND or maybe some custom thing you'd like to invent, is expressively complete if it allows us to build all Boolean formulas. That is, given any Boolean formula with any number of inputs and any number of outputs, it can be constructed with only the set of logical connectives that you provide. So for example, the set containing logical AND, logical OR, and negation is expressively complete. We can build any formula we want only using those three. And why is that? We can prove this using the fact that we can express Boolean formulas using sum of products. If we look at the majority circuit we talked about before, for this we've got the truth table, and we wrote out the rows where the output is true in the form of a sum of products. In principle, we could do this with any Boolean formula. Regardless of how many inputs or how large the truth table is, we can just enumerate all the possible combinations that make the output true, using ANDs to connect the variables together, and then logical ORs to connect what represents each row of the truth table together. And because this is only using ANDs and ORs and negations, that means this set of operators is expressively complete. You might ask, do we include brackets as an operator? Well, no, not really. The brackets is just indicating order of precedence, which things we evaluate first. So the brackets don't really count as a logical operator. So this is not a very useful definition if you're trying to prove if a particular set is expressively complete, because you have to prove all possible Boolean formulas, like this one, can be written in that form. So because we know the set containing AND and OR and negation is expressively complete, we can use this to have an equivalent but more useful definition of expressively complete. So we'll use this one instead when we're checking if a set is expressively complete. So a set of logical connectives is expressively complete if we can define the operators OR and 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 negation using those logical connectives. So if you can manage to build these three things, then you know you can build any other formula in general by doing sum of products. So let's do an example. The NAND operator, that is the not AND operator, so it does the logical AND and then negates afterwards, which is sometimes denoted by a little up arrow, or other times it's denoted by like a vertical pipe, depending on context. This operator all by itself is expressively complete. And so we'd like to prove that. And so the way I'm going to prove it is I'm going to step by step construct these three operators, because as soon as I've constructed one, I can use that operator to help me construct the others. So here's the proof. So the first thing I need to do is I need to construct negation using NAND. And thankfully that's easy enough, because if we recognize the fact that something NAND with itself, so X NAND X, well, by definition, that's the negation of X and X. And if X is false, false and false is false. And if X is true, true ANDed with true is true. So X and X is the same thing as X. So we can see, using the NAND operator, I can define negation. Okay, that's one of the three done. But now I can help myself here by using the NOT operator to build up other things, because I know in principle the NOT operator can be built out of NANDs. So we've done NOT. Let's see if we can build AND. Well, if I've got NAND, AND should be pretty easy, because NAND is the negation of AND. So if I can just negate it twice, that'll like undo the negation that NAND creates, right? So if I want to create X and Y, well, that's the same thing as negating X and Y twice. So the negation of X and Y. And this part in the middle, that's just the definition of NAND. So we have the negation of X NAND Y. And I don't need to go any further. I don't need to break up this negation, because I know in principle this thing can also be built with NAND, so we can stop here. And so the last thing I've got to build is X or Y. And that's not so obvious how I'm going to go about doing that. But thankfully I can cheat a little bit here and use De Morgan's law to help me. Because I know X or Y can be written as negation negation x, and negation y. What does this mean, like, intuitively? If x or y is true, an equivalent way of saying that is it's false to say x is false and y is false, right? If this statement here is true, it's not the case they're both false, then at least one of them's got to be true. And then I don't got to go any further because I know I can build nots and I know I can build ands, so I'm done immediately. Okay? So, because I can build these three connectives, and because of the argument before, that means I know I can build any Boolean formula. That makes the NAND connective expressively complete. So, as an exercise, I'd like you to show that the set containing the implication operator and the NOT operator is expressively complete. As a hint, I mean, the negation's already done because you've got negation to begin with, so you get this one for free. So essentially what you have to show is you need to show you can write x and y in terms of something using only implications and nands, only implications and nots, I should say. And once you've got that, you get OR for free. Alternatively, if you construct OR using only implication and ands, using implication and, why do I keep saying nands? Implication and nots. If you can build either of these two, you get the other for free, because we know from De Morgan's law, x and y is the same as not x or not y, and x or y is the same as not x and not y. So depending on the set of operators you got, it might be easier to build and then just get OR for free. It might be easier to build OR and then get AND for free. So depending on the operators you got, one might be easier than the other.